Hello and welcome to the Project Explained channel. Today in this video we'll be going over AP Chemistry Unit 8, which is about chemical equilibrium. And just to start, we'll be going over a quick overview about what chemical equilibrium is. So let me just write out this example reaction to start. So we have 2 NO2 gas, and then that will go to 2 NO gas and then plus O2 gas. And essentially the important thing to notice here is that instead of in our normal chemical reactions that we've been seeing up until now, we've seen that the arrow just simply goes from left to right like that, indicating that we're going from our reactants on the left to our products on the right. But in this case, as you can see here, we have 2 arrows, one going in either direction. That essentially means that this reaction is reversible. So meaning we can start with these products over here and then we can react them to get this reactant, or we can start with this reactant over here and go to these products here. So that's essentially what a reversible reaction is. And and what equilibrium is, so at equilibrium, so equilibrium is essentially like a state. So at equilibrium, the rate of the forward reaction, and the forward reaction is essentially us going from left to right. So in this case, it would be going from NO2 to NO and O2. And so the rate of the forward reaction is equal to the rate of the reverse reaction. In this case, we're going from right to left. So the reverse reaction in this instance would be going from NO and O2 to NO2. And another important thing to note is that at equilibrium, the concentrations, so I'll just write cons for short, concentrations of the reactants in the products are no longer changing. So not changing. And just to give a better visual on what that would look like is essentially if I were to graph, let's say I was to graph concentration versus time. So again, I'll just abbreviate that, concentration versus time of the reaction we were looking at above. So essentially, let me just graph this here like this. I'll say that the y-axis is concentration, the x-axis is time. Essentially what's going to happen here is, well, if we look back at our equation, we know that as the reaction proceeds, going from left to right, the concentration of our NO2 is going to go down because we are using it up to create a product. So if we go here, I'm just going to draw my curve for my NO2. It's going to look something like this. Let me draw that a little better. It's going to look something like, it's going to look something like this. So as you can see, over time, our concentration of NO2 is going down. It'd actually probably be a little more steeper than this, but we'll just say that this is an estimate. And then if we go back to the equation, we have NO and O2 as our products. So meaning as time goes on, more of those concentrations will go up because they are being produced. So I'll just draw my NO here, and I'll draw something like that. So we'll say this is, let me draw that a little more accurately. There we go. So I'll say that this is my NO, and then this was our NO2. And finally, we also need to draw our our other reactant, which was our O2. So I can draw something like this for my O2. And the reason why the NO curve is steeper in this case is because for every mole of O2 that we're producing double the amount of NO. So that's why, as you can see here, this has a bit more of a steeper curve here than this does there, if you were wondering about that. So I will label this as my O2. Now, the important thing to notice here is that if this graph was drawn a little better, at a certain point, these three lines, these three curves would flatten out. And I could say that would be maybe somewhere around, I could say that that would be maybe somewhere around here. I can draw a dotted line. And at this point, all of these concentrations will flatline. So essentially they'll stay constant. And that's essentially when so this right here, this is our equilibrium, because as we said before, if we go back up here, we said rate of forward reaction and rate of reverse reaction are the same, but also that the reactants and products, the concentration of them is not changing. So as we look at this graph, we can see that at a certain point in time, right here specifically, our concentrations are not changing. So that would be like an example graph of what that would look like. And there are other, just to give you a quick look at some of the other ways that these graphs may look. So what we had was sort of a graph that looked like this. Let's say I had only one reactant and one product. I would say like about here is where we're hitting equilibrium, is right there. And by the way, this graph is in time versus concentration, or concentration versus time. You could also technically have something look like this. All that really matters is that at some point these two curves are flattening out, and that's when we know our concentrations are not changing and that we have reached equilibrium. And then to look at some other graphs, you could have something where instead of concentration versus time, we have rate of reaction versus time. So in this case, we could say that our forward rate, as we know, as a reaction proceeds, it slows down. So our forward rate could start here, and then over time it'll just flatten out. I know this line is not exactly the best, but you get the idea. And then we have our reverse reaction, which obviously would start slower and then speed up over time as more of our product is available to react to go the other way in the reaction. So as we can see, sort of over here, this is where we're getting our equal rates. So this is where we're getting our equilibrium. This is what equilibrium would look like on a rate versus time graph, because like we said before, forward rate equals reverse rate. The forward reaction rate equals the reverse reaction rate, and that's when we're essentially achieving equilibrium. And so the next thing that we want to go into is essentially what our equilibrium expression looks like. So let's say I have the reaction JA plus KB, and then I have my two arrows going in the opposite directions, of course, indicating that it is reversible. Remember, we cannot have equilibrium if the reaction is not reversible. I'll say LC plus MD. So essentially how we're going to write our equilibrium expression is that it's always going to start with the letter K. And this letter is known as our equilibrium constant. And we'll get more into K and its different characteristics later. But let me first start out with how we solve for K. So essentially, we're going to take the concentration of our products. So products is going to go here. And then concentration of our reactants. Reactants will go in the numerator. And so if I look here, I will see that, okay, so I'll get the concentration of C, and I'll raise it to the power of its coefficient. So in this case, L. So C raised to the power of L. I know that's kind of bad, but we'll just leave it. And then we have oops, I wrote this wrongly. This should be actually this should be m and then d. So, and then it'll be d raised to the power of m, and then we'll do the same for the reactants. So we have a raised to the power of j, and then we have b raised to the power of k. So pretty straightforward. You just need to make sure that your reaction is balanced, so that you're writing the proper coefficients. And just for some extra detail, this k is, if you ever see something called kc, that's the same thing as just k. Essentially, let me just go through an example here. If we have nitrogen gas plus hydrogen gas, and then that would go to NH3. Essentially, if we were to write an equilibrium expression for this, we'd first start with our k, so we know k, and then that would be equal to, remember, we're going products over reactants. So I'll just do prod over react just for short. So essentially this would be the concentration. Remember, we're doing these brackets here. That means concentration. We're not looking at moles or anything else. So essentially it'd be NH3, and then to the power of 2, and then I would have N2, the concentration of N2 times the concentration of H2. And that's how you write your equilibrium expression. So now more going into k. So k is a constant. K is a constant, and k is a constant for a given balanced reaction like we had up here, where we had a nitrogen hydrogen gas reacting to make NH3, and the thing that will affect k. So k is affected by temperature. So affected by T. I'll just put T for temperature. And essentially, as long as, no matter what concentrations of these reactants that we had for this specific reaction up here, our K value is going to remain the same. So even if we're given different concentrations for N2, H2, and NH3, the K value is going to be the same for all of those. So essentially there's close to an unlimited number of possible combinations of concentrations that you could put in here for this reaction and then get the same K value out of it. So let's talk about what K exactly means. So let's say that we have a K value that's large. Well, remember that K is essentially a ratio of products over reactants. So if we have a large K value, that means that we have a lot of products and not that much reactants, which essentially means that this will mean that most reactants, I'll just put react, converted to products. So essentially we would consider this product favored, and so this would be a K value. A large K value could be if K is greater than 10, something like that. And then on the other hand, if our K value is small K value, again going back to this ratio up here, products over reactants, well, that essentially means that we have a small amount of products and then a large amount of reactants. So that essentially tells us that I would just say not. I would say very. Okay, we'll go with very little reactant converted to products. Converted product. So that's essentially what a large and small K value would mean. So in terms of now manipulating K with different equations and stuff like that, let's say that we had 2NO2 gas, and then that's going to be, the reaction is going to be something like this: 2NO gas and then plus oxygen gas. Oh yeah, and then one other thing I wanted to mention up here when we're writing our equilibrium expressions, one thing to note is that these values here, it's for species in the gas phase and the aqueous phase. Solids and liquids do not contribute to the equilibrium expression. It's very important to note that. You definitely want to look at the states of your species when you're looking at a reaction and writing your equilibrium expression, because you don't want to include those solids and pure solids and pure liquids in the equilibrium expression. So now moving on. So we have this equation here, and let's say that we learned earlier in Hess's law we can manipulate equations, or we can multiply them by a factor of something, or we can flip them. Let's say, for example, I was to say that this has a k value of something, right? Let's say this has a k value of x. We don't know the k value, we're just going to say it's x for now. Let's say I was to then write a different expression, O2, so I'll do 1/2 O2 gas plus NO gas, and then that, let's say that goes to NO2 gas. So if we look here, what have we done? Well, the first thing I can notice is that, well, this used to be 2, now this is now 1. This used to be 1, now this is 1/2. So we multiplied by a factor of 1/2. So when you do that, when you multiply the chemical equation by like a factor such as 1/2, you're going to raise your k value to that. So it would be essentially k to the 1/2. So going back here, if we're saying that k is equal to x, well, now we're going to say that our k prime is equal to x to the power of 1/2, which is essentially just us saying root x. And then the other thing that we did was we reversed the reaction. So when you do that, then you're going to reciprocate k. So essentially, let's say I have k. That's going to become 1 over k when I flip the reaction. So if our original k constant was x originally, well, now we're gonna take the square root of that and raise it to the 1/2, because we multiplied the equation by a factor of 1/2, and then we're going to reciprocate that. So that would be essentially 1 over x. This is our new k value with this manipulated chemical equation right here. Okay, and then the other thing that I wanted to go into was the concept of Q. So Q is our equilibrium. It's the equilibrium reaction quotient. So quotient. Essentially, what Q is that let's say that we're given a set of concentrations at some time, and we don't know if the chemical equation is at, or the system is at equilibrium at that time. So if we don't know that, then we can essentially use the same expression as we were before. So if I just go like this is what we had before. Remember, we're taking concentrations, and then we're going to raise them to the coefficient of these species. So for example, it was JA, so this would be raised to the power of J. Then we have B, K. So that's Q. So essentially it's K, but we're just at a different time, and we don't know if we're at equilibrium. Now, how do we use K to figure out if we're at equilibrium? Well, if Q is equal to K, and K is the equilibrium constant, then that essentially means that we're at equilibrium. We're at equilibrium. If Q is greater than K, that means that our system is going to shift to the left. So left. We're going to shift to the left. What does that mean? Well, if we're saying that Q is greater than K, that means our Q value has more products. So if we're just saying, let's say we're going like this, reactant is going like this, and then on this side is a product. If our Q value is greater than our K value, that means that we have more product. because remember K is product over reactant, and so is Q. So essentially, in order to get rid of that extra product, we're going to have to shift to the left, so going towards the reactants, so that we can get rid of our excess product. And sort of in the opposite way, if our Q is less than K, we're going to shift to the right. So what that exactly means is that, well, in this case, we have our Q is smaller, so remember, products over reactants, we have more reactants then. So if we have more reactants, then we need to get rid of that extra reactant somehow. So that means we're going to shift to the right so that we can get rid of the reactants and then produce more product. So that's essentially what Q is. And most of these problems that you'll have with Q and K are just simple math and plugging in numbers and then just making sure that you're doing all of that correctly. So the final thing that I want to get into is the concept of an ice table. So an ice table essentially helps us go through helps us determine what concentrations we'll have at equilibrium. So if we take, for example, this reaction here, we'll say H2O gas plus CO gas goes to H2 gas plus CO2 gas. And essentially, I encourage you to, I'll say the problem and the specifics of the problem in a second, but I encourage you to try to do this problem on your own if you know how to do the ice tables, and then see if you get the same answer. So essentially, our K value for this is given, it's 2.0, and we are also given that we're starting our starting concentration. So our starting concentration of H2O is 8.0 molar, and then our starting concentration of CO is 6.0 molar, and we need to figure out the rest of the concentrations at equilibrium. So how I'm going to do this is I'm going to set up an ice table. So what is an ice table? So if you know how to do an ice table, I encourage you to pause and then try this yourself. But essentially what I'm going to do is, I know initially, so ICE stands for initial, change, and then equilibrium. So I know that initially we're going to be starting with 8.0 molar. Our concentration of of water is going to be 8.0. And then I know for CO it's going to be 6.0. So I'll do 6.0 here. And I'm not starting with any reactants, so for the I'm not starting with any products, so for the two products it'll be 0 here and 0 here. So now we've done the I part of ice, we've done the I part. So now it's time for the change. So here you're going to be adding or subtracting by X. Essentially, let's say that, so all of these coefficients here are 1, 1, 1, 1. So I don't need to worry about having any coefficient in front of my X. So all I'm going to do is we're going to subtract X here, we're going to subtract X here. Remember, because the products, we're losing reactants so that we can convert it into products. So that's why it's minus X for the reactants. And I'm going to do plus X here, and then I'm going to do plus X here. So now for my equilibrium, I know this is going to be 8 minus X, I know this is going to be 6 minus X, and I know this is going to be X, and then this is going to be X. So now I have my equilibrium, essentially concentrations. So now all I need to do is write my equilibrium expression. So I know my K is equal to 2.0, and then remember, we're going products over reactants. So here's my products, so I'm going to do X times X, and then I'm going to do 8 minus X, and I'm going to do 8 minus X, or sorry, not 8 minus X, 6 minus X, oops, 6 minus X here, just like that. And then if I get out my calculator, and I do recommend that you guys one quick trick for this is that if you have a TI-84, you can go to math and then go up one, and then you have numeric solver there. And all you're going to do is in the first one, for this one specifically, you can enter in 2. And then for the second one, you can enter in x squared, because x times x squared divided by 8 minus x, and then times 6 minus x. So x squared divided by 8 minus x, and then times 6 minus x. And then once you do that, all you're going to do is hit enter, and then you should click alpha and then click solve, and it should give you 3.99. So we'll say x is equal to 4. So just like that, without doing a lot of math and algebra and all of that, we just use the numeric solver to get x is equal to 4. So we're not done yet though. We still have to substitute this back in to find the equilibrium concentrations. So now we know that our equilibrium concentration for water is going to be 8 minus 4. So that's just going to be 4 for water. And then for our CO gas, it'll be 2, because 6 minus 4 is 2. And then for our hydrogen gas, it'll just be x, and we know x is equal to 4, so this will be 4. And then for our CO2, it'll also be 4. So that's how we get our equilibrium concentrations from using an ice table. So that was pretty straightforward, hopefully. One thing to remember is that in other problems, possibly more complicated problems, if I was to have like a coefficient of 2 here, 3 here, 1 here, and 1 here, I would need to do minus 2x and then minus 3x. So just make sure you're moving that coefficient down there when you're subtracting x, so the math works out properly. So now going into the last concept of the unit, which is Le Chatelier's principle. So I'll just write Le Chat for short, Le Chatelier's principle. And all it really states is that if we are changing something with the system will try to go back to equilibrium. So Le Chatelier's principle essentially refers to these things as stresses. You could just think of them as something is changing in the system is at equilibrium, it likes to be at equilibrium, but then you're changing something, so now the system wants to go back to equilibrium. So there's 3 stresses that we need to worry about. One is a change in concentration. So essentially I'm adding or removing some of the product or reactant, and then as a result of all these stresses, the system is going to essentially compensate and try to go back to equilibrium in one way or the other. So the first one is change in concentration. The second one is change in pressure. I'll just write change in P. And then the third one that we'll discuss is our change in T. So I'll just use one simple equation to quickly explain all 3 of these different stresses and how they affect the equation. So let's just say A plus B, reversible reaction goes to C plus D. Okay, so first stress, we're changing concentration. What if I remove some A? So I'm going to remove some A. Okay, so now I've removed some A. So some A has been removed. Now we're out. Now we've knocked the system out of equilibrium. How does the system get back? Well, to get back to equilibrium, it needs to add some A. How can we add some A? Well, to add some A is a reactant. We have to take some of this. We have to take some of this product and then convert it back into reactant. So if we remember from before, the terminology for that is shift left. So I just draw an arrow like that. So I would say shift left. And let's say, let's say I will decrease, let's say I increase D, increase the concentration of D. Okay, so now we were in equilibrium, but now we've added extra D, and it's unwanted. So how do we get rid of that? Well, we're going to take D and we're going to convert it back into reactant to sort of level out the reaction and then get back to equilibrium. So how do we do that? We need to take some of this D and then convert it into reactant. So essentially, all we're going to do is we're going to get rid of some D here, and then we're going to, if we get rid of some D, or sorry, if we're increasing D, so we want to get rid of some of it. So essentially then we're going to shift left, because in order to get rid of the extra D that has been added in, we need to shift to the left and convert that into reactant to get rid of that. So that's change in concentration. So change in pressure is also fairly straightforward. Let's say that I'll go back and I'll sort of use the same reaction that we were before, that whole A plus B equals C plus D. So let's say I do 2A plus B goes to 3D plus 2C. Okay, so the main way that we're going to increase or decrease pressure, we know that pressure is inversely proportional to volume. When our volume goes up, our pressure goes down. When our volume goes down, our pressure goes up. So let's say that I decrease the pressure of this system. Decrease P. So I've decreased the pressure. How do we get back to equilibrium? Well, the main way that we get back to equilibrium is going to be by shifting to the side with the most moles of gas, so that when we do that, more moles of gas will increase the pressure, because remember, N is directly proportional to P. So I want to increase the pressure because we've just decreased it. So to get back to equilibrium, I need to increase the pressure. So I'm going to look here and I'm going to say, okay, I have 5 moles here and I have 3 moles here. So in order to get the pressure to increase, I need to shift towards the side with the higher number of moles. So that means that we're going to be shifting right. Let's say I increase the pressure. This is pretty obvious, but it would be the other way, because if I increase the pressure, I want to now lower it more. I want to lower it so that we can get back to equilibrium. So that means that we'd be shifting to the left, and that's essentially how pressure would work. So now the third and final thing that I want to go over in this unit is just another stress of Le Chatelier's principle, and that is going to be change in T, which is a little more confusing. So essentially what change in temperature is going to do is it's going to affect our K value. It also will affect our K value, and you'll see why in a second. So how this will work, let's just go back to A plus B. A plus B goes to CD. Let's say that the delta H for this reaction is less than 0. Well, that means that it's going to be a negative delta H, which means that it's exothermic. So technically I could write over here plus energy. So you can just write out energy over here as if it's a product. That's perfectly fine. So now I have to sort of think about what would happen here if our temperature is changing. So let's say our temperature goes up. How is our K going to be affected? So it's pretty simple in that, let's just say if our equation, or if our reaction is in this case exothermic, increasing the temperature is going to, so we've now increased this temperature here. We're going to want to get rid of some of that energy. So we're going to have to shift, we're going to have to shift to the left to get rid of that energy. So essentially, we're shifting left, meaning we're creating more reactant and we're losing product, which means our K value is going to go down. And the same goes for if our temperature is going down. Well, we've now lowered our energy over here. Now we want to gain some of that energy back to get back to equilibrium. So we're going to shift to the right, and our K is going to go up because we're going to have more product and less reactant now. So let me just change the situation here and say, well, what if our delta H is greater than 0? Well, now it's a little different because we're no longer, this is now an endothermic reaction, meaning that we have to add energy. So energy is going to be on the reaction side, so it's just going to be energy plus A plus B. So now what happens if I increase the temperature? If I increase the temperature, now we want to go to so now I've increased the temperature, and now I want to get rid of some of that extra energy. So that means that in order to get back to equilibrium, we're going to have to shift to the right. What does shifting to the right do? It increases the products. Increasing the products increases our K value. So it's so our K goes up. So now in this case, for a endothermic reaction, temperature and K, as temperature goes up, K will go up, and as temperature goes down, K will also go down. Because if we think about it this way, if we lower the temperature, we've essentially lost energy, and well, not lost energy, but we need to essentially regain that somehow. So the system will compensate by shifting to the left, which will essentially create more reactants, and we'll lose some products, which is why the K value goes down. So that was the last thing that we're gonna cover in Unit 8, and I hope that this video was helpful.